Hi everyone, it's my pleasure to share the recent process and our recent works in the quantum random number generation or the QRNG for short. Quantum information by the quantum mechanics and the information types and it's often referred to as the second quantum revolution. Quantum mechanics has been developed for over 100 years with famous concepts like quantum superpositions, like Schrödinger's cat, and the quantum entanglement, which won the Nobel Prize in recent years. Until the 1960s, Richard Feynman posed the question: what kind of computer are we going to use to simulate physics? This really kick-start the field of the quantum information. Today, it integrates the principles like the entanglement, quantum measurement graphs, low Chloe survey with the application, the computing, secure communication, AI, so on. The field gained widespread attention when Shaw proposed an algorithm that allows the quantum computer to break the RSA encryption. This has led to a breakthrough in the quantum computation, which can be beyond the classical computing power limit. And the quantum communication we enable in unconditional secure communication. And the quantum measurement pushing the boundaries of precision. Overall, it employs the new quantum phenomena and theorems such as the quantum decoherence, quantum entropy theorem, and the quantum phase transition, and so on. The main goal of quantum information is to achieve practical quantum devices. QRG stands out as one of the most important and mission for wide application. So why do we need QRG? Random number core resource in information and size used in simulation, cryptography, data type, and even daily application like gaming. And a dual random number generator, RNG, should have statistical properties, ensure privacy, for a high generation rate, and be easy to achieve. Traditional pseudo-RNG generates randomness through the algorithm, but they are not too random. They have some problems which compromise their statistical properties and privacy. In contrast, QRG uses the quantum phenomenon for true randomness. Randomness in QRG comes from one rule. The collapse process of superposition state is inherently random process that cannot be predicted. For example, varying diagonal polarization with polarization beam slicker (PBS) triggers this collapse and can generate the randomness. This provides certified randomness. Even with full knowledge of the current device and the unlimited computing power under the quantum mechanics, it's impossible to predict the next random number. And there are already commercial products out there like IDQ's QRG USB and the Samsung mobile phone, which integrate the QRG right in it. QRG can be classified in various ways beyond the diagonal polarization method with PBS. Other types include measuring the P temperature of the vacuum state, or varying the phase graduation in the laser. In our recent work, we have proposed using the randomness from the Raman background scattering in the single mode paper, combined with the time and the frequency randomness, achieve a rate over 4 millibits per second. The examples above are fully trusted device QRGs, where the randomness depends on the assumptions about the device themselves. To reduce the assumptions, we can look at the device-independent QRG, where the randomness doesn't rely on the device at all. It's hard to accomplish and typical at a low rate. So to have a trade-off between the practicality and the randomness, we turn to the semi-device independent QRG, or semi-DI QRG, which use the partial assumption. Recent semi-DI protocols are based on the different assumptions, such as source independent, variable independent, dimension weightless, or energy bound. Among these, the earliest and most attention protocol source independent, environment divided energy. They estimate the untrusted components, so test from the trusted part. However, real devices are usually bad, which can lead to the overestimating of the final randomness. To address this, our recent research explores two main paths. One is to establishing a model for some specific sections, and the other is design new protocol bypass characterization of the devices. Start with the first part. We considered the effect parameter environment devices for the sorted vector, such as the output, the detection, dependency mismatching. To characterize this, we modeled the response probability with these functions, like this equation. And we then calculate the mean entropy for the with this response probability. Here we account for the maximal unbalance caused by the infections, and use the idea from the quantum error correction. This allows us to first derive the mean entropy for the ideal source. That's the first equation. And then extend this to untested source with the quantum error correction at the second equation. Finally, we get the effect on the final data effect and run the simulation for the different infections. These results show that this infection can cause a significant reduction in the randomness rate. Through this, we have provided a secure bound that account for these infections. Since the infections can largely reduce the randomness, our previous work, we want to explore a way to minimize this impact and develop a new model for getting a higher rate. In this work, we shift the infection effect to the error rate rather than the response probability. Here we first pose a lemma that the bound probability for different measurement using the trace distance, and use it to bound the theoretical error rate with the effect randomness generation basis. Here, use this method, we can partial correction of the achieve partial correction of the infections for different bases in the 2D type system, which can prove the final rate. In following simulation and experiment, we found that compared to the existing work, our protocol adversely improved the randomness rate. Even with a large infection, we can achieve randomness generation rate over 3 millibits a second. Previous works have focused on combination models for the specific infections, providing a secure rate under those conditions. However, it's possible we include all of the possible fraction models. So this motivates us to shift toward design a new protocol to bypass the detailed characterization, rely only on the necessary particle assumption without need every parameter of the fraction. First, we propose quantum channel method to connect the assumption. Here, we try to relate the assumption from the source element, the QRG. For the source element QRG with a fully polarized environment and untreated source, we establish a quantum channel, transfer the environment interactions to the source. And we have proved that such channel always exists, and the equation show here. This transforms the original protocol with the source original protocol, such as we consider untreated source and POM into a new protocol with untreated source but the projector. Then we focus on estimating the randomness with this new protocol to the projective measurement basis. We apply the triangle equality, which is similar to the lemma in our previous work, to convert the non-orthogonality of basis into the error rate and derive the final randomness rate. That's way we get a new protocol with the untreated source and the dimensional uncorrelated POM. This protocol has relaxed the environment assumption of the source independent protocol. And we have implemented this protocol using the everyday atoms like laser and bomb, and achieving rate over 1 millibit per second with laser and 70 kbit per second with bomb. And the previous work require a two-dimensional environment assumption. But as we know, the two-dimensional environment are harder to achieve than the two-dimensional source. So we, in following, we try to develop a protocol some two-dimensional source instead. Since the high-dimensional environment will introduce the extra noise. Here we find that we need purity bond to help us to remove this extra noise. We discovered that for a 3-state and the one environment, we can bound the randomness relative value C by the observable quantities with the help of the geometry properties of the Bloch vectors under the assumption of the purity bound. So we can use it to find the final random instrument. We then connect this value C to the guess probability using some theoretical method such as the cavity of the gas probability and the duality between the source and the environment. This results in a protocol with 3-qubit input and that only require purity bound and one fully untracted high-dimensional environment. In the experiment, we simulate the state using current source and achieve a rate over 40 kbps. In conclusion, we have addressed the key problem. Real devices are usually in fact in the semi-device dependent QRG. Our solutions for the two parts, combination, more precise model with addition no parameter, minimize the infection and randomness, and design a new protocol with fewer assumptions, more practical setup, and higher rate. In Phony, I think we also follow these two paths to get more researchers. Besides that, when we look hard, new physics and platform may introduce fresh opportunity to solve ongoing challenges in QRG field. Finally, I want to thank all our collaborators for their contribution to this works. That's all I want to introduce in this talk. Thanks for listening.